So today we're going to finish up what we started talking about on Wednesday and continue on our material about alcohol. So last time we talked about physical properties of alcohols. We talked about the fact that hydrogen bonding is a major factor in the physical properties that we see. We learned that the more substituted the alcohol, that is primary versus secondary versus tertiary, right? The different types of hydrogen bonding that we get. We get strong hydrogen bonding with what type of alcohol? Primary, right? And it has to do with steric hindrance, right? And so as we go to secondary and tertiary, we would expect to see the hydrogen bonds become weaker and weaker due to steric hindrance, and we would expect that to have an effect on the boiling points and other physical properties. Then we started talking about making alcohols and ethers, and we talked about SN2 reactions with hydroxide. So hydroxide can displace a primary alkyl or a halide from a primary alkyl halide and generate an alcohol. But we can also generate ethers using a similar process. And what was the name of that reaction? It's the Williamson ether synthesis. And we know that the Williamson ether synthesis is the reaction of an alkoxide with an alkyl halide. And typically there are primary alkoxides and primary alkyl halides. And so through SN2 chemistry, we can do an awful lot of stuff. We also learned that we can add water across the carbon-carbon double bond, which we learned back in 255, but we were kind of refreshing our memory about that, right? We can add water across a carbon-carbon double bond. That's typically acid catalyzed, right? We go through a carbocation and we have to worry about rearrangements in those cases. However, there's another thing that we can do to add water across a carbon-carbon double bond that avoids rearrangement. Does anybody remember what that is? Hydroboration oxidation actually does do that. However, that gives us anti-Markovnikov alcohol. So that's a good example, but not the one I'm thinking of. The oxymercuration demercuration sequence. We'll add water across the carbon-carbon double bond just like as if you were using acid. It gives you a Markovnikov alcohol. But it avoids rearrangement because we never have a carbocation, right? And so some examples that we talked about last semester, right, was we can take 1-hexane and do the oxymercuration demercuration sequence, and we can get the Markovnikov alcohol in good yield, right? So that works really well, good yields, right? We can take 1-methyl-cyclopentene, oxymercuration demercuration sequence, we can get the 1-methyl-cyclopentanol, again a Markovnikov product. Nothing particularly surprising there. We can take this substrate, 3,3-dimethyl-1-butene, do the oxymercuration demercuration sequence, and again get essentially a quantitative conversion to the Markovnikov alcohol. The important thing about this last one, though, however, is if we tried to do this reaction with sulfuric acid, would that be the product that we would get? It would not. And why would it not be? We would have rearrangements, because why? What would happen? We would do what? We would have a methyl shift. So if we looked at the substrate, right, the first step in reacting this with acid is that you protonate the alkene, and we would get a secondary carbocation, which is okay, but this substrate can actually rearrange to a more stable carbocation by shifting one of those methyl groups. And so we would go from a secondary carbocation to a what? To a tertiary carbocation, very good. And so we would end up not getting the product that we see here. And so that's why it's important to have this tool in our toolbox to give Markovnikov alcohols this oxymercuration demercuration sequence. Okay? So again, the Markovnikov product. And again, we know that we are not going to go through a carbocation because this experiment tells us that we didn't generate a carbocation, because the cardinal rule of carbocation states that if a carbocation can rearrange to a more stable carbocation, it will, right? And so we know we don't have that as an intermediate here. The stereochemistry of the oxymercuration reaction, it proceeds with an overall anti-addition. So if we look at this alkene that's cyclic here, in the first step, the oxymercuration step, we're going to add what across the carbon-carbon double bond? What gets added in the oxymercuration step? It's in the name. We add the mercury and we add the oxygen, right? We're going to add an OH and we're going to add the mercury in the first step. It goes through a mercurinium ion, right? Mercury bears the formal positive charge. There is no carbocation, right? The way that we have it drawn here is a little strange. It makes it look like these two bonds are of equal length, but we know that that's not true. One of those bonds is weaker. And remember, weaker bonds are longer bonds. Which one of those is the weaker bond? The one to the most substituted carbon or the one to the least substituted carbon? It's the most substituted carbon. Because that mercury is positively charged, it is pulling electrons to itself as if it were electronegative. And it can pull more electrons from that more substituted bond closer to itself because that would put a partial positive charge on a carbon that is more substituted. And that's better, right? We know that that's better. Do you have a question? Oh, okay, just scratching your head. Okay. And now what happens, of course, is the water attacks the carbon that has the weakest bond, right? And we form the oxymercuration species. And so you can see here that the OH and the mercury are anti to one another. Very similar to how we saw bromohydrin formation with bromine and water, right? That gave anti-addition as well. So nothing really new here. Okay? Then in the second step, we have the sodium borohydride under basic conditions. We call this a reductive cleavage step, which actually cleaves this bond and replaces it with hydrogen. And you end up with the Markovnikov product shown there. So over two steps, it's the same thing as adding water across the carbon-carbon double bond. All right, alcohols can also function, as bases and nucleophiles, and why is that? Why can an alcohol function as a nucleophile? It has lone pairs of electrons, and so it would be a Lewis base. We know that all nucleophiles are Lewis bases, but not all Lewis bases are nucleophiles, right? And so alcohols can function as bases and they can function as nucleophiles. And it turns out that alcohols react with strong acids, as you might expect. If you take a strong acid and you place it into water, what happens? It dissociates, right? So if I take HX and I place it into water, I get H3O plus and X minus. So what would you expect if I took a strong acid and I placed it into alcohol? It will dissociate as well, and it will give us a protonated alcohol as the H3O plus equivalent, if you will, and X minus. So that happens, right? We end up protonating in strong acid, and we form the oxonium ion, ROH2 plus. And in fact, we found that that was a necessary intermediate in some of the SN1 reactions that we talked about last semester. Right? Now, OH2 plus, is that a good leaving group or not? It is a pretty good leaving group, right? Not too bad. It can leave as water, and water's a pretty good leaving group, right? Why do they have the equilibrium lying to this side as opposed to over here? That's exactly right. Remember, the equilibrium always lies to the weaker acid, weaker base pair, right? So we end up with the alkyl oxonium ion, assuming this is something like HCl or HBr or something like that, right? You'd end up forming this species, okay? Now that we have that alcohol protonated, we have a pretty good leaving group. And one can imagine that that some nucleophile could come in and react in like an SN2 fashion and displace water as a leaving group, and you can form a new carbon nucleophile bond. In theory, we can do that, but there are some problems with that. Can anybody tell me what the problem might be? What else could the nucleophile do? It could also react as a base and remove one of those acidic hydrogens, right? So this really only works for certain nucleophiles. You can't throw just any old nucleophile in there and get this to work, because acid-base chemistry almost always is faster than any other kind of chemistry we know of. Transfer of a proton is very, very easy. And so, yes, we can do this type of chemistry, and I'll show you some examples of it. It turns out that we have competing processes. You can have nucleophiles that attack carbon and function as a nucleophile, but you can also imagine the nucleophile reacting at the hydrogen and just protonating the nucleophile. So if I have a nucleophile that's a really strong base, this chemistry doesn't work in an SN2 fashion. It just does acid-base chemistry. And so we're going to need other reagents that can convert the alcohol into a good leaving group. And we'll talk about those today as well. So let's talk about the conversion of alcohols into alkyl halides. Okay, one of the common transformations is to take an alcohol and convert it into an alkyl halide. Pretty easy to do, actually, with the strong acids. There are a few reagents that do this that you all need to have committed to memory. If you like studying with flashcards, this is a point at which you need to start building flashcards based on reagents and what they can do. You need to know that the hydrogen halides can do this type of chemistry, so HCl, HBr, HI. HF does not do this. HF is not a strong enough acid. The phosphorus halides, like PCl3 or PBr3, those types of reagents can convert an alcohol into an alkyl halide. And thionyl chloride, SOCl2, which is probably one of my favorite reagents for doing this. It can convert an alcohol into an alkyl chloride very, very easily. So you need to have these reagent classes memorized, and you need to know if you see them, oh, that can convert an alcohol into an alkyl halide. That's the first layer of that onion that we talk about that we have to know. You need to know what the reagents can do. What would be the second layer of that onion? There's the what, and then there's the, which is also known as the why, or the how, right? You need to know that. Actually, science answers how, not why, right? But it's the how it occurs. So what occurs is kind of that first level of understanding, and then you need to know how it occurs. And so we'll focus on that. Easiest way, an alcohol going to an alkyl halide, that's the what? What reagent do I need to do that? Now we're going to talk about the how these things work. Okay? So let's look at some examples. Let's suppose we take butyl alcohol and we react it with HBr gas, hydrogen bromide. What's going to be the product of that transformation? What are we going to get? We're going to get butyl bromide, right? We are going to end up with butyl bromide. Now notice it says dry HBr gas or sodium bromide and sulfuric acid at reflux. What happens if you take sodium bromide and you take it, I mean it's a salt, and we kind of sprinkle it into sulfuric acid? What would happen? You get hydrogen bromide. That's exactly right. So both of these are actually hydrogen bromide, okay? It just turns out that a lot of times scientists like to use, or chemists I should say, like to use sodium bromide and sulfuric acid because sodium bromide is a solid, sulfuric acid is a liquid. We know how to handle those very, very easily, right? HBr, pure HBr is a gas. It means I've got to have a gas cylinder, I've got to have a regulator, I've got to have tubing, I've got to become a plumber, right? But with with sodium bromide and sulfuric acid, I just need a graduated cylinder to measure out the liquid, and I need a scale to measure out the sodium bromide. So a lot easier to handle sometimes than dealing with these gases. Here we're taking propyl alcohol, HCl zinc chloride, and we're going to heat it up. And by the way, concentrated HCl and zinc chloride is known as Lucas reagent. It's another named thing that you need to know. And it's really good at converting primary alkyl halides into, or primary alcohols, excuse me, into primary alkyl chlorides. And so here we get propyl chloride. Now you might be asking, why do we need the zinc chloride? We'll talk about that a little bit more in a minute. But the zinc chloride actually activates the alcohol because is chloride a better nucleophile than bromide? Or is it a worse nucleophile? It's worse. As we go down the family, right, the nucleophilicity increases. Chloride is just, it's all right. It's kind of sluggish. Will this reaction work without zinc chloride? Yeah, but it'll be really slow. Throw in some zinc chloride. That helps speed the reaction up. And the guy who came up with this, his last name was Lucas, and so they call it Lucas's reagent. Tert-butyl alcohol, reacting it with concentrated HCl at 25 degrees, very easy reaction, and you end up with this product called tert-butyl chloride. Yes, sir?
I was going to ask what the condition reflux was like.
Okay, reflux. Can anybody answer that? What does reflux mean? It means to heat it to boiling.
Okay.
But to reflux, you have a condenser on top of it that takes everything that's boiling and it recondenses it and brings it back down into the flask. Right? So I think you all did some refluxes last semester in lab. You should have. Right? So that's what that is. It's heating something to its boiling point and then recondensing it so that you don't lose it. Okay. This reaction is actually kind of fun to do. So concentrated HCl, as you know, is mostly water. Tert-butyl alcohol, is that going to be soluble or insoluble in water?
Soluble.
It's soluble because it satisfies what rule? The 5-carbon rule. So when we start off with this reaction, the way that we do this in my lab when we need to make tert-butyl chloride, and we've done this reaction a few times since I've been here, you take a separatory funnel. You all have used those before, right? You put in so much HCl, whatever volume you need, let's say 100 milliliters, and then you add the tert-butyl alcohol to that, and everything looks like one homogeneous layer. You shake it up a little bit just to make sure it's good and mixed, and you set it in the hood. What happens over time? Yeah, it separates out. It actually turns out that it doesn't drop out. It rises up. It forms a second layer. Because why? That's alkyl halides are not soluble in water, right? And so we go from something that is completely soluble in water to something that is insoluble in water, and we see that second layer form. So after about 10 minutes, we see a second layer form. We drain off the bottom water layer, and I've got pure product sitting up there at the top. It's the easiest reaction in the world. Nobody can mess it up. The only way you can mess it up is by dropping your separatory funnel and it goes all over the floor. But the reaction, you can't mess this one up. I mean, you mix it together, you shake, you put it in the ring stand, you come back in 5 or 10 minutes and you've got product. Drain off the water, take the tert-butyl chloride and do whatever you need to with it. Easy, easy reaction. Okay? I wish every reaction was that easy. But they are not. Okay, so we're going to continue talking about converting alcohols into alkyl halides. We'll continue on talking about converting alcohols into RLG. What does LG mean? What is that an abbreviation for? Leaving group. So converting an alcohol into some other kind of leaving group that we can use for other types of chemistry. Okay? And then maybe we'll have time to get into the synthesis of ethers today. So let's go ahead and get started. So let's look at some observations about reactions of alcohols with strong acids to form alkyl halides. We know that the reaction is catalyzed by the acid. We get the acid back. We know that if we add acids that are stronger than HX, the reaction gets sped up. In other words, if I have HCl, what would be a stronger acid than HCl? H2SO4. So we can add a mixture of HCl and H2SO4 to the reaction, and the reaction speeds up. We can notice that. We notice that carbocation rearrangements occur in just about every case except for the reaction of primary alcohols. So secondary alcohols will show rearrangements, and even tertiary alcohols can show rearrangements. Okay? But primary alcohols, typically we don't see any rearrangement. Meaning what? No carbocation, right? And why not? What do we know about primary carbocations? They're very, very unstable. So they usually don't get generated, right? So for example, if we take our good friend 3,3-dimethyl-2-butanol, which we would make from this alkene using oxymercuration, demercuration, right? If we take this and treat this with a strong acid, like HCl, we don't just replace the OH with the Cl. We actually see a rearrangement occur. And that's because that protonated alcohol leaves. I generate a secondary carbocation. That then rearranges to a more stable carbocation before the chloride attacks it. Okay? We know that there is a reactivity order for the alcohols. I know that when I react an alcohol with a hydrogen halide, like HCl or HBr, that tertiary alcohols react faster than secondary alcohols, react faster than primary alcohols, and primary alcohols react a little slower than methanol. That's the reaction order. Okay? Can anybody tell me why methanol would be faster than a primary alcohol? Okay, so let's look at it over here on the board. So if we have a primary alcohol that's protonated, and the nucleophile has to attack here, right, and break that bond. Now we think about that versus methanol that's protonated. What's different? You're right, it's about the structure, but what about the structure? Why would this be slower than this? You guys didn't tell me, I forgot an arrow. And why does that matter? Two words. Steric hindrance. If in doubt, blame steric hindrance, right? It's always a good go-to. But yeah, the nucleophile coming in here, this methyl group can get in the way a little bit. Here, there's no other substituent. It's just little tiny hydrogens. This reaction will occur faster. They're both SN2 reactions because I can't generate a carbocation from either one of them, but this one's going to be a little slower than the reaction with the methanol. Okay? Now, what about the tertiary? So why is the tertiary alcohol faster? Is it going through an SN2 reaction? It is not. It's going through what? SN1. It turns out they're pretty quick because the SN1 only depends on the concentration of the alcohol. It does not depend on the concentration of the nucleophile. SN2 reactions depend on both concentrations, right? And so we will see reactivity differences because of that. Okay? So if we think about the SN1 mechanism, so we take something like a tertiary alcohol like tert-butanol, right? We've placed it in our separatory funnel with our HCl. We've shaken it up. We've put it on a ring stand, and we're watching it. As the reaction is occurring, what's happening, right, is that the alcohol is getting protonated. We end up with a protonated alcohol. This is a reversible reaction. It's an equilibrium. The equilibrium typically does lie to the right. The stronger the acid, the more to the right it sits, right? Anytime you have an alcohol and a strong acid, this is the first step you need to do, is the protonation of the alcohol. Now, we've got a tertiary carbon here that is attached to the oxygen. Can we do SN2 chemistry? Will a nucleophile come back here and displace that? No, right? That doesn't happen. So this has to wait for the water to leave, and this is the slow step. Water leaves, I generate the tertiary carbocation, which is drawn kind of funny in the slides, right? I've just done a bond cleavage, generated a carbocation. At this point, I ask myself, can that rearrange to a more stable carbocation? What's the answer? No. So we've got a good carbocation, and now the chloride comes in and reacts with the carbocation, forms the tert-butyl chloride, and the reaction is complete. Now notice all of these reactions are reversible. However, the reaction goes to completion. In other words, I put this in my separatory funnel with my HCl, all of this gets converted to this alkyl chloride. What is driving this equilibrium to completely go to product? Come on, I know it's Friday. What is it? What's driving the reaction here to the right? It's Le Chatelier's principle, but what specifically is allowing Le Chatelier's principle to work here? It's insoluble, and so it separates away from the reaction. That's effectively removing the product from the reaction, which drives the reaction to the right. Okay? Now, you do have to worry about a competition between dehydration and substitution. So, for example, if I take tert-butyl alcohol and I treat it with a strong acid, I get that protonated alcohol, obviously, right? I get a carbocation intermediate, but I can have two pathways, right? I could have my nucleophile functioning as a base, giving me the alkene, or I could have my nucleophile functioning as a nucleophile and giving me the product. So if I want to convert this to product, I told you that we do this in a separatory funnel in a hood. So what's the temperature, high or low? It's pretty low, right? And we know that lower temperatures favor substitution. However, if I took that separatory funnel and I don't know, took a blowtorch to it and heated it up, right? What's going to happen then? We're going to start favoring the elimination pathway because I know that eliminations are favored by higher temperature, right? And it turns out that this particular alkene is actually a gas. And so as I heat it up, the gas can bubble out, and that drives the reaction in that direction. So anytime we have an SN1 reaction, we also have to think about E1 competing and vice versa, right? So we have to keep that in mind. Now, another thing, if I wanted this to completely go this way, and I didn't really want to heat it up a whole lot, there's another possibility, and that is I can use a dehydrating acid. Sulfuric acid is my favorite dehydrating acid. It likes to remove water as opposed to functioning as a nucleophile, because HSO4- is a very poor nucleophile, so it dehydrates. It removes water from an alcohol to form an alkene. There were a couple of other acids that we learned that were dehydrating acids. Can you remember them? So sulfuric acid is one. What's another one? Para-toluene sulfonic acid. What'd you say? And phosphoric acid, concentrated phosphoric acid. There are others, but those are the three that you need to remember. Sulfuric acid is a dehydrating acid, concentrated phosphoric acid is a dehydrating acid, and para-toluene sulfonic acid is a dehydrating acid as well. Okay? HCl is not a dehydrating acid. Chloride's a pretty good nucleophile. It's not great, but it's pretty good. And if we keep the temperature low, we can do substitution. If we heat it up, we can do elimination. So we need to keep reaction conditions in mind. So on an exam, if I gave you a tert-butyl alcohol plus HCl, and I asked you for the product, what would you assume about the reaction conditions? Pardon? Why would you assume that? What would you assume about the reaction conditions? It's at low temperature. You always assume ambient temperature, room temperature, unless I tell you otherwise. So if I don't tell you the temperature, you assume it's room temperature. If it has to be really cold, I will say like minus 78 or extremely cold or something like that. And if I tell you that it needs to be at higher temperature, I might say something like reflux, or I might say 100 degrees, or I might say 200 degrees, something along those lines. I will indicate to you what the temperature is if the temperature is relevant to the reaction. Okay? If I say nothing about the temperature, you always assume it's ambient temperature, which is approximately 25 degrees Celsius in South Mississippi on a nice day. South Mississippi in the middle of summer, it's not 25 degrees. Just a little hotter than that. All right, let's think about the SN2 mechanism a little bit. So let's take methanol and react it with concentrated HBr. So I have methanol. I'm going to react that with HBr that's concentrated. It means that it's HBr in water, right? But it's concentrated. What's going to be my first step? What's going to happen? Help me push the arrows. I'm going to protonate the alcohol. How am I going to do that? And what else? Yeah, right? So that's going to happen. And we end up with the protonated alcohol. Can I generate a carbocation now? I can't, can I? Methyl carbocations are extremely unstable. They don't form under normal conditions. This is kind of normal. Doesn't happen. Okay? Now what happens? The protonated alcohol has converted that oxygen into a pretty good leaving group, right? And now what can happen? Help me push the arrows. Where do I start? Bromine, bromide, right? And what happens? Attacks the carbon, and then what happens? And that all happens at the same time, right? It is a single step. It is the slow step. And we end up forming the methyl bromide and water as the leaving group. Okay? Notice this is a reversible step, but they show this as irreversible. Can anybody explain to me why? I'm sounding like a broken record today. Whose principle? Le Chatelier's principle, but why is it driven so far to the right that they ignore the reverse reaction here? Why is that? Is methyl bromide soluble in water? Nope. What else do we know about methyl bromide? Number one, it's not soluble, but number two, it's a gas at room temperature. So it's an insoluble gas. It's going to just sit there and bubble out of the water mixture. And so the reverse reaction is impossible because it's no longer in contact with the reaction. Okay? So even though theoretically it's possible to go in reverse, the practicality of the reaction, the fact that this is insoluble and it's a gas, means that it will not revert at all. Okay? Does anybody know what methyl bromide is used for? Not so much in the United States anymore, but in a lot of developing countries, they still use methyl bromide as a fumigant. It is a very powerful alkylating agent. Alkylating agents react with DNA and cause things to die. You do not want to alkylate your DNA because you'll die. You will get cancer and all these kinds of things. But it's good fumigants, and they do use these types of things still to fumigate for things in the developing world. In the United States, we've gotten away from it because it is such a powerful carcinogen, because it's a powerful alkylating agent. But some countries still do use it. And I think the number every year is going down who uses it. but it's a powerful fumigant. Okay? All right. You all know all that stuff. All right, so we can convert alcohols into alkyl halides with hydrogen halides. We know that. I also know that HCl is a slower reaction than HBr is a slower reaction than HI. Can anybody tell me why? Why does the rate of reaction increase as we go down the family? That's true. I is big. The leaving group in all of them would be the same. Water. Okay, so we know that nucleophilicity increases as we go down the periodic table. So if we're talking about an SN2 reaction, that explains some of the rate, right? But what if it's an SN1 reaction? The nucleophile never comes into the rate equation. Nonetheless, HCl is still slower than HBr, is still slower than HI. What also increases as we go down the family? Acidity. And as we increase the acidity, what happens to the protonated alcohol concentration? Increases or decreases? It increases, right? Because we know that the equilibrium is going to lie to the weaker acid, weaker base pair, right? And so the more protonated alcohol I have at equilibrium, the more leaving group I have, right? Faster the reaction will occur, okay? So we know that as we go down the family, HCl, HBr, HI, it increases going down. HF doesn't really work for this. HF is not a strong acid, remember? All three of these are strong acids because they all completely dissociate in water. HF does not. And so you have to have other types of chemistry to convert or to make alkyl fluorides. Primary alkyl halides with HCl, the reaction is really slow. So slow it's actually painful. Painfully slow. But you can speed it up using Lucas's reagent, which is just adding zinc chloride to concentrated HCl. And what happens here is that in the first step, the oxygen actually complexes with the zinc, and you form a zinc-oxygen bond. That makes this a really good leaving group. And so it kind of compensates for the fact that chloride is a fairly poor nucleophile. It really weakens this bond. And so chloride can then come in and easily displace this in an SN2 fashion, and you can form the alkyl halide, plus you get this zinc species that is the leaving group. Anybody know anything about zinc and oxygen? Are those bonds strong or weak? What do you think, given what I've just told you here? Do you think the zinc-oxygen bond is strong or weak? Weak? Strong. Zinc-oxygen bonds are really strong. Okay? And it turns out probably most of you have used this to your advantage. If you're ever at the beach and you put the white gunky stuff on your nose to keep it from getting sunburned, does anybody know what that is? It is zinc oxide. Okay, and zinc oxide blocks the sun, and it lasts forever because the zinc-oxygen bonds don't break down. But you look funny because you got this goopy white nose walking around. But it works really well, right? Zinc-oxygen bonds are actually quite strong. That's why this can actually form this intermediate fairly easily. Zinc loves oxygen. So I want you to take just a couple of minutes with your partners, and I want you to solve these three problems. So I'll give you 2 minutes. I want you to give me the products. You need to think about the mechanism, but you don't have to give me the mechanism. All right. What do we get in the first reaction? Give me the name. Propyl bromide. What propyl bromide? 1 bromo propane. What is the mechanism? It is an SN2 mechanism. Second one. 2-propyl chloride or isopropyl chloride. Either way, I don't care. HCl, zinc chloride. What's the mechanism? This one is most likely SN2 as well. Okay? We can't know that based on the product that we get because we'd get the same product whether it was SN1 or SN2. But what leads us to think that it's going to be an SN2 reaction? What's strong? Well, there's no chance of rearrangement, but that could still go through an SN1. What do we need for an SN2? We need a good nucleophile. Do we have that? Chloride's just okay. But we also need a good leaving group. And what happens when we add the zinc? We convert that into a really good leaving group, right? So we have a really good leaving group. It's secondary. Could be SN1, could be SN2, but I'm going to bet on SN2. Okay? Given that we have a really good leaving group. Now, question 3. Let's see, what are we doing? HCl. What are we going to get for the products? Or product? So what are we going to get? And just that? What kind of mechanism must this be? This has to be SN1. Why must it be SN1? I've got a tertiary carbon. I can't do SN2. So this gets protonated, it has to leave, and I get a carbocation. The carbocation has what kind of geometry? Trigonal planar. So the chloride could either come from either side, the top, which would give this one, or it can come from the bottom, which would give the other diastereomer. Will it give us these in equal amounts? That's what I want you all to think about over the weekend. I want you to come up with an argument as to which one of these you think would be the major product from this reaction. Use whatever resources you want. I'll give you a couple bonus points for it if you put it on a 3x5 note card and you're correct. Turn it in on Monday. Okay? But I want you to think about this last reaction. Which one of these is the major product? And explain to me through mechanism why you predict the major product to be the major product. Okay, so it's all about making a good argument. All right, have a good weekend. I'll see you all on Monday.